Hello, welcome to Basics of Finite Element Analysis. Today is the last day of this third week of this particular course, and in the last class we had just started discussing numerical integration, and what we are going to discuss today is the Gauss quadrature method of numerical integration. So, again our aim is that we want to compute this integral f of x dx, and this I can perform the same integral in the natural coordinate system by doing three things: changing the limits to -1 to 1, expressing f in terms of zeta. So, we know that x is a function of zeta. So, this is what we do, and then the third thing we do is that dx gets replaced by the Jacobian for the eth element and times d zeta. Now, this entire thing could be written as another function f hat, okay, and this depends only on zeta times t zeta, where f hat zeta equals f of x, which is a function of zeta, times Jacobian of eth element. Now, earlier we had shown that, so this is an integral, so I can call it some I, right, this is an integral. Earlier we had seen that for trapezoidal way of integrating and Simpson's rule of integrating, I could express I as nothing but a sum of f of xi times wi's. This we had shown earlier. Where xi was what? It was the quadrature point and wi was the quadrature weight, and r minus 1 was the polynomial order. Okay, it was the polynomial order. So, this integral can also be expressed in same terms. This integral can also be expressed in similar terms, in terms of weights and quadrature weights and the function, the values of the function at quadrature points. What is f of xy? It is the value of that function at quadrature point, right. For instance, for trapezoidal rule, for trapezoid, what was the function? I was f1 times h by 2 plus f2 times h by 2, where f1 was the value of that function at first node in the x coordinate system. See, this is about natural coordinate system, but the trapezoidal rule works in the x coordinate system. So, in the x coordinate system, f1 was the value of that function at first node and f2 was the value of that function at the second node, and h2, h is the element length, h1, h by 2 is the first quadrature weight and h2 is the second quadrature weight. So, similarly here also, but here the domain is the natural coordinate system, but the same thought process can work here also, it is just that the domain has changed from -1 to 1. So, I can write it as t is equal to 1 to r, just putting a new index, f of zeta I, and it should not be f but it should be f hat, where f hat is this thing, f of x expressed in terms of zeta times Jacobian times, oh I am sorry, actually I will keep it, I will write I itself, times Wi. So, if we know these Gaussian quadrature weights and if we know the location of these points, see in case of trapezoidal rule, the location of the points was the first point and the last point, that is where we had to calculate. In case of Simpson's rule, the 3 points were first point, mid point and last point, right. In Gaussian quadrature also, I mean using Gaussian quadrature also the same thing is there. We have to find out the value of at some number of points and also the associated weights for those points. So, if we know this information, then I can very easily calculate the integral of this function f(x) dx over the domain. So, I will again write it here, I from a to b f(x) dx can also be written as -1 to 1 f zeta d zeta, and this equals f hat, which is a function of zeta I, f hat evaluated at location zeta I times quadrature weight, and this summation is going to happen from 1 to r, it is going to happen from 1 to r. So, this r is a third parameter. See, m was one parameter, it was about the transformation, n was second parameter, it was about the variable, how it varies. Here r represents how many points we are going to integrate it, this right, it represents how many points we are going to integrate it. I can integrate it at 1 point, 2 point, 3 point, 4 point and so on and so forth, right. So, that is why it is a third index r. So, here zeta I is ith quadrature point, f hat zeta I is value of f hat at zeta I, and Wi is quadrature weight. Now, in trapezoidal rule, so there is a very fundamental difference between Gauss quadrature and trapezoidal and Simpson rule and some other integration schemes. So, in trapezoidal rule, if this was the element the quadrature points so this is for trapezoidal rule. Were same as nodes, right? For a linear element, the trapezoidal rule is where we have two nodes. So nodes were xa and xb, and that is where we calculated f1 and f2. In Simpson's rule, xa, xb, and this is the mid node, and its location was xa plus xb by 2. Here also, same as nodes. Okay. In Simpson rule also, the same thing is true. These points, quadrature points, are known as base point. They are also known as base points. But in Gauss quadrature, first one is quadrature points and nodes are not same. We will show that. This is very important. Second is these points are unequally spaced. Unequally spaced. Okay. We'll show that. I'll give you some examples. We'll show that they are not equally spaced. Okay. So quadrature points and nodes are not same. This is a very important distinction. Very important distinction. So this zeta I value will not be same as that of the node. It will not be same as the node. This is important to understand. So we will write this. So what are these points and what are the weights? So like in this case, we had 2 quadrature points, then we had 3 quadrature points. You can have also a rule for cubic. You can have another where we will have 4 quadrature points and so on and so forth. So now what I will do is, so basically when you are increasing the number of quadrature points, what is changing? R is changing. When I am increasing the number of quadrature, and as R changes, the integration becomes more and more accurate, And if R exceeds a particular value, then it becomes exact. We will see that. First, we will look at this table. Table for Gauss quadrature. So So, zeta values varies in the from between what limits? Zeta -1 to 1, okay, R, and these are weights. So, if R is equal to 1, if R is equal to, so first case will be R is equal to 1. If R is equal to 1, it is essentially what? Constant, right? Order of polynomial will be n minus 1, right? R is equal to 1. The location at which you have to calculate this f zeta, that location will be 0, zeta is equal to 0. So, it will be in the center of the element, okay, and the weight will be 2. So, if you are using one quadrature point to do the integration, what will you do? If you are doing one integral, f hat evaluated at 0 times that weight function, weight number, which is 2, understood? Then you say, oh, I do not like it, I want to be more accurate, okay. So, R could also be made 2, and this table can grow very far, okay. So, if R is equal to 2, then you have to evaluate the function at 2 locations. The first location is zeta equals 0.5773, and the second location is zeta equals minus 0.5773, and the weights are 1 for both of them, okay. So, in this case, suppose you are using 2 Gauss quadrature points to do the integration, then what will you do? You will use this formula again. You will evaluate f hat at how many locations? 2 locations. The first location will be when zeta equals minus 0.5773, and you will multiply, you will get some number, you will multiply that number with 1, and then you will add that to f hat evaluated at plus 0.5773 times 1, okay. So, that is there. Then you can have 3 Gauss quadrature points. Here the first Gauss quadrature point is 0, and the second Gauss quadrature point is plus minus 0.774596. Now, how do these come? I mean, we are not going to discuss in this thing, but just as we said that Simpson rules, we directly explained that. We directly wrote down the Simpson rule, but if you find, you can go and explore literature to find the mathematical basis for this. But so this is the third. So, when R is equal to 3, then you have 3 Gauss quadrature points. One point is located at 0, and other 2 points are located at plus minus 0.774596. Okay. So, they are not equally spaced. It is not that between the 2 nodes all the Gauss quadrature points are equally spaced, right, because here the first node is at minus 1 and the first Gauss quadrature point is at minus 0.77. So, there is a difference of 0.23, and then the next Gauss quadrature point is at 0. So, the difference is 0.77. So, things are not equally spaced, and the weights are 0.8888, and for these two guys it is 0.55555, and so on and so forth. If your function is more complicated, then you can use Gauss quadrature for R is R is equal to 4. Here we will have 4 Gauss quadrature points. These 2 points are 4 are plus minus 0.339931 or 81 and plus minus 0.861136. Again, they are not equally spaced, and the weights are 0.65 0.214 and 0.347854. And there are, you can have 5, 6, 7 and so on and so forth. But the point is that you can, using this table, if you have this table, or you can give this table to your computer program, right, and you tell it that to the computer program what is the value of r you want integration for, then for that value of r you can implement this formula very easily, right. All you have to do is find out this value of f hat at Gauss quadrature points, right, f hat at Gauss quadrature points, multiply that by wi, wi is given here, and once you have multiplied it by wi, those products you add them up and you will get your integral, okay, you will get your integral. Now the question is, what r should we choose? What r should we choose? Okay, what r should we choose? So the answer for that is, so if I choose r is equal to 100, maybe the answer will be accurate, but if I increase the number of Gauss quadrature point, what happens? I have to do more computation, because we are talking about maybe lakhs of elements, right. So for each element, if I go from r is equal to 1 to 2, number of computations double. Here they go 3 times when I go to r is equal to 3. So I have to make sure that I use the value of r which is minimum and it still gives me accurate results, okay. So the choice of Gauss quadrature points depends, so what r should we choose? So you choose, so first thing is find p. What is p? P is the order of polynomial in f hat, okay. In f hat it is the order of polynomial. So that you can figure it out. For instance, example, suppose your Kij is equal to xa to xb, ax d psi I over d psi dx times d psi j over dx times dx. Suppose this is your stiffness matrix definition, and let us say that ax is constant. So I can replace this ax by a naught, right, and if I am assuming, see what are these psi's? They represent the variation of u over the domain, है ना. If I assume that u is linear, then what is the variation of d psi over dx? Constant, है ना. D psi over dx is constant. So it is, because of d psi over dx my polynomial order is 0, because of this d psi over dx I still have 0, because of a I still have 0. So overall polynomial order is constant, okay. So now then in that case 0 plus 0 plus 0 is, and what is dx? Dx is je times d zeta, right, and what is je? It is a, for straight elements it is constant, we saw that, we wrote that earlier. So je is also constant, so this is, iska bhi order 0 hai, So, what that means is that P in this case is equal to 0. If P is equal to 0, so this is the first step. Another case, it could be, let us say Mij is equal to xa to xb, let us say b x psi I psi j dx. So, in this case, let us say let bx is equal to b naught plus b1 x, suppose. Then what is this? First order psi I, let us say psi I is linear, we choose linear interpolation functions, then this order is 1, this order is 1. So, total order kitna ho gaya? It becomes P is equal to, P becomes cubic in this case, right. So, first step is you find out P, then second find R using P. If P plus 1 is even, then R equals P plus 1 by 2. Okay? If P plus 1 is odd, then R is equal to P plus 1 by 2 plus half, because R cannot be a fraction. So, you go to the next order. So, this is how you figure out R. So, I think this closes the discussion for today's week. We will continue this discussion maybe for one or at the most 2 more lectures in the next week about Gauss quadrature, and we will actually do some examples so that all of you become familiar and more comfortable of how to use Gauss quadrature for integrating functions. And once we are done, then we will move to some other topics in FEA. So, thanks a lot for your time, and I look forward to seeing you tomorrow in the next week. Thank you very much.